Hello everyone, welcome back to another lecture video. In this one we will be studying the design of couplings. So we already studied about the shaft and their design, where shaft is used for transmitting the power. So whenever the shaft is too long, so instead of using this too long shaft, we will be having different shaft and we will be interconnecting. So coupling is a device used to connect two shafts together at their ends for the purpose of transmitting power. And in this one we will be designing the rigid couplings. So rigid couplings means this will not allow any misalignment between the shafts. So if the shaft available are perfectly aligned, or they are having very accurate alignment in between them, that is no compensation of misalignment is permitted, then this will be known as rigid coupling. So example for rigid coupling is a flange couple. So you can see in this figure, so these components are known as flange. So these two flanges are connected by use of this bolt, and this shaft is connected to the flange at the hub portion, and shaft and hub is connected by the use of key. About key already we have studied. So this is known as flange coupling, and this is an example for the rigid coupling. So we'll be studying the design of this rigid coupling in detail in this video. So in this one you can see the assembled view as well as the components of this flange coupling, which is a rigid coupling. So here shaft is there, so shaft is actually rotating, this will be transmitting power, and this shaft is connected to key. So this one is the key, where half is coming in the shaft and remaining half is coming in this portion. This is known as hub. So you can see here, this is the shaft and this is the key, which is getting into the key slot or keyway in the shaft, and remaining will be lying onto the hub portion. And this is known as the flange, and this one flange is being connected to the another one with the help of bolt. Usually 4 or 6 number of bolts are used to connect between the two flanges. So these are the bolt connection you can see. So these are the bolt which are getting inserted into this holes. And finally the power transmitted from shaft through key to this flange will be transferred through bolt to the other flange, and finally this will be transferred to this shaft by along this key which we are using here. So this is the line of power transmission in this coupling. Here you can see the two types of flange couplings. One is known as unprotected type and another one is known as protected type. So the figure is shown here. This is from this data book. You can see the figure numbers. So unprotected type means the bolt ends are open to the surrounding. That means this is very risky to the workmen who are working with these couplings. So in order to give the safety for the operator, this end will be protected, or the projections of this coupling will be coming in such a way that it will be covering this bolt, and that is known as protected type flange coupling. So we have already seen this figure. Here you can see this bolt end is coming within this end of this flange. That means this is actually coming under this protected type. So the design of this protected as well as unprotected type flange coupling is similar. The design means we have to evaluate all these parameters. That means here you can see values D, D1, D2, D3, L. So different parameters are there. Here also you can see. So by design of this flange coupling means we have to find value of all these parameters. So first step in this one will be, here we have to find this diameter, where D is the diameter of the shaft. Also all remaining parameters you can represent in functions of this diameter D. So we will be seeing in detail while solving a problem in this video itself. So here you can see the design procedure for flange coupling. So design of flange coupling means first we will be evaluating the size of the shaft, then the size of hub portion will be evaluated, then the key to be used to connect the shaft and hub will be found, and then the bolts which are used to connect, the size of the bolt, number of bolt will be evaluating which are used to connect these two flanges which are coming in coupling, and also the size of flange end of this coupling will also be evaluated. So these 5 steps are the design procedure, and this design procedure will be discussed in detail by solving a problem. So let's get into the problem. So here we have a problem to design a cast iron flange coupling which is transmitting a power of 18 kilowatt at 1440 rpm. The allowable stresses for shaft, key, bolt, so all are of same material. In shear is 75 megapascal and in crushing is 150 megapascal. The allowable shear stress for cast iron flange material is 5 megapascal. So according to all these given details we have to design. So already I have mentioned that first step will be to find the shaft diameter. So here you can see this is the shaft, and in this figure also this is the shaft, and its diameter is represented by capital D. So you have to evaluate this shaft diameter. So shaft diameter will be evaluated based on the load that it is transmitting. Here the load acting is only due to the power transmitted or the torque transmitted. So from the power equation, so power you are having, power is equal to 2 pi nt divided by 60. Here power is given in kilowatts, so you can convert it into watts. So it is 18 into 10 raised to 3 watts, and the rpm is 1440 rpm. So from this you can evaluate the torque which is transmitted. So if you are solving, you will be getting the torque transmitted as 119.38 Newton meter you will be getting. So torque is 119.38 Newton meter. From this you can evaluate the shaft diameter. So this will be creating shear stress, and the magnitude of shear stress you have already seen. So the magnitude of shear stress is 16T divided by pi into D cube. So you can evaluate this, already torque value is there, and this should be lesser than the allowable shear strength of the shaft material. Here this shaft material property is 75 megapascal in shear. So this should be substituted in SI unit. So it is 75 into 10 raised to 6. So torque already you are having. From this you can find the value of this diameter. So if you are solving, the diameter of the shaft you will be getting in SI unit, then you can convert into the in mm. So you will be getting 20.08 mm, and this is equivalent to, so we will be standardizing it, and finalized standardized diameter of the shaft will be 22 mm. So this is the final diameter of the shaft, or the value of D to be used. So the next part to be designed is hub. So hub is the portion which is coming in contact with the, or which is making a connection between the shaft with the help of key. So hub portion you can see in this figure as well as in this figure, and hub is having two dimensions or parameters. One is hub diameter, that is here in this figure you can see this is the hub diameter which is represented by capital D1, and the hub length, that means the length of the hub portion, that is this much length, and it is given in terms of L. So this is the hub length. So here for finding these two parameters we are having the equations in data book. The hub diameter you can see here in equation 13.1t in form of D1, and this is an empirical relation in terms of the shaft diameter capital D. And also the hub length you can see here, L is given by this expression. So we will be making use of this expression. So first we will be finding the hub diameter. So it is equal to 1.5 times D plus 25 mm. So here we have to substitute this D in mm. Then you will be getting the value as 58 mm for the hub diameter. So hub diameter is 58 mm. Next we will be finding the hub length. So hub length is L is equal to, you can find the equation, it is equal to 1.2D plus 20 mm, and if you are substituting you will be getting 46.4 mm you will be getting, and this will be rounded to next even number, that is 48 mm will be the hub length that we are selecting. So these are the two parameters for the hub. So now we have discussed or the design two components or two parts of this flange coupling. Next we will be seeing the third one. So third one is the design of key. So keys are used to connect the shaft and the hub portion. So you can see here key which is used, or in this figure you are seeing the key. So in the right shaft key is coming here, and the left one or the second shaft key will be coming here, which are used at 90° for effective connection. So here it is mentioned that the crushing strength, you can see in question, crushing strength is 150 megapascal and shear strength, allowable shear strength is 75 megapascal for the key material. So sigma crushing is 2 times that of shear. So in such a case we will be using square key, and we have to find the dimension of the square key to be selected. So the dimension of square key can be found from table 4.1. So here we will be selecting a suitable key for the shaft which is having diameter of 22 mm. So in the first row you can see for shaft diameters, here you can see this range 70 into 22 means for shaft from 17 up to 22 you will be taking this value. That means the size will be equal to key cross section 6 by 6 value you will be taking. So for the square key you will be selecting the width is equal to 6 mm and the height is equal to 6 mm. So key is having three dimensions. One is B, one is H, and then there is one is known as length, that is length of the key. So since key is inserted in within the hub with respect to the shaft, so the length of the key should be equal to the hub length, that which we have already evaluated. So this must be equal to 48 mm. So here we have evaluated the dimensions of key also, 6 by 6 mm cross section square key with a length of 48 mm. Next we will be making a check for the stresses induced in this key as a result of power transmission, to make sure that the stresses induced are lesser than the allowable strength of the material. So check for stress in key will be made here. We already studied that the failure of keys are occurring by two modes, by shearing and by crushing. So already we are having the equation for the in form of the torque transmitted equal to half into tau is the shear stress induced in the key, L, B and D is the shaft dimension, L and B are the dimensions of the key. So all values you are having. So you can substitute all the values and you can find the value of the shear stress induced in the key. And if you are substituting these values in mm, that in SI unit, that means this torque is equal to 119.38 Newton meter. The length of the key is 48 mm. So this must be equal to 0.048 meter. The B is equal to 6 mm. So this is 0.006 mm. And diameter is 22 mm. So it is 0.022. So if you are substituting all these values, then you will be getting the shear stress in pascals, or you can convert into megapascal. So tau 1 you will be getting 37.68 megapascal. And the allowable shear strength of the material given is 75 megapascal. So this is 75 lesser than 75 megapascal. So according to this failure criteria, we can say that this design is safe. In a similar way, the allowable crushing strength was given as 150 megapascal, and by using this equation you will be finding the crushing stress induced, that is sigma c, by substituting all the values. So if you are substituting here, actually in this equation 1 by 4 into sigma c into d into h into l, where this d is actually the shaft diameter. So this is actually the capital D. So if you are substituting, you will be getting the crushing stresses 75.37 megapascal, and for this material the allowable crushing stress is 150 megapascal. So here also the condition is satisfying, so it is also safe. So both the failure criteria which are coming under safe condition, thus the selected dimension of key we can finalize. So the dimensions of 6 by 6 and the length of 48 we can use, because it is clearing the check for stress in keys. Next we will be seeing the fourth component of the flange coupling, which is the bolt. So in design of bolts, we will be finding the number of bolt required, diameter of bolt to be used, and the pitch circle diameter of bolt which are coming on the flange we will be evaluating. Then we will be making a check for the stresses induced in bolt, and will be looking whether it is satisfying or whether it is lying in the safe region. So first here you can see the bolt which are used. So bolt are used to connect the flange. This will be inserted into this holes, and then we will be tightening with this nut for making the assembly. So here also you can see the bolt. So bolt is having the dimension, diameter, and the number of bolt. In this figure you can see one bolt will be coming here, another one will be coming here, another one here, or here. Usually 4, 6 or even number of bolt are used. So we are having the expression for finding, empirical relation for finding the number of bolt, that you can see here in equation 13.1a. I is the number of bolt. You can use either of any of this equation. So here we will be finding the number of bolt I using 3d divided by 80 plus 2, where d is the shaft diameter that we evaluated at the beginning. So this shaft diameter is to be substituted in mm, that is equal to 22. So if you are solving this one, you will be getting a value of 2.83, and we will be taking since this is a number of bolt, we will be taking the next higher even number, that is the number of bolt to be selected is 4. Next we will be evaluating the size of the bolt, that is diameter D. Already we have seen this diameter. So for finding the diameter also we are having an empirical relation given in 13.1. See, you can substitute. So diameter you will be using this equation 0.423 D divided by square root of I, where I is the number of bolt, which is 4 we have finalized, plus 7.5 mm. So here all values to be substituted in mm. So this D is actually 22 mm. Then we will be getting the bolt size as 12.15 mm. So this also we will be standardizing and we will be taking the next value, or you can take the standard size of the bolt from the data book for the chapter of bolt, and this one you will be finalizing as 14 mm. So the size of the bolt used is 14 mm. Next we will be evaluating the diameter of the bolt circle. Diameter of the bolt circle means, so this bolt are coming in a circular manner and this diameter of the bolt circle is known as D3. So D2. So then this figure also you can see the D2. So this is the pitch circle diameter of the bolt, and for finding the bolt this pitch circle diameter you can use this equation 13.1e. So here we will be evaluating the diameter of bolt circle D2, which is equal to D1 plus 3.2 times D, where D is the diameter of the bolt. Then you will be getting approximately around 105 mm you will be getting. So this is the pitch circle diameter of the bolt. So now we have evaluated the different dimensions, number of bolt as well as size of bolt and the pitch circle diameter. Next we will be making a check for the stresses induced in the bolt. So for making the check for stress induced in the bolt, we will be evaluating the shear stress, and for which you will be making use of this equation, the torque capacity based on shear. That means the expression is given in terms of torque, and in the right hand side the shear stress tau is coming. I have rewritten this equation here, so this will be used for making a check. So torque value you are having, tau is the shear stress to be found, I is the number of bolt, D is the size of bolt, and D2 is the pitch circle diameter, and then you can substitute all these values and find the value of this shear stress. So if you are substituting all units properly, then you will be getting the shear stress which is induced in the bolt as 3.69 megapascal, and the allowable shear strength of the bolt material is 75 megapascal. So hence the design is safe. So here also we are getting a safe condition. So the check for stresses in bolt is also completed. So next we will be looking for the design of the last component, flange. So in this figure you can see the flange. So flange is the element which is used or which is connected with the help of this bolt. So these are coming at the ends. So here you can see the flange, as well as here also you can see the flange. So the two parameters or dimensions of flange is, one is the outer diameter of the flange, that means this much diameter. So it is designated or represented by letter capital D3, and in this figure also you can see this one, this is D3. And the next parameter is thickness of the flange angle or flange thickness. So this is the flange thickness T. This is shown in here also. So the equations for this one you can find here in 13.71F and 13.71H. So I will be evaluating the outer diameter of the flange D3 using this equation. This is equal to D1 plus 6 times D, where D is the size of the bolt, and finally you will be evaluating, or you will be getting this D3S 142 mm. So this is the outside diameter of flange. In a similar way you can find the flange thickness T also. So T is equal to 0.35 D plus 9 mm. So if you are substituting, D will be substituting as 22 mm, then you will be getting around 17 mm. The whole digit number you are getting is 17 mm you are getting for the flange thickness. So the dimensions of flange are also found. Next we will be, as a final step, we will be making a check for the stresses in the flange. So for checking the stresses in flange, we will be finding both crushing stress in bolt and flange and the shear stress in flange. So equations required you can see here. For evaluating the crushing strength, you will be using 13.2D, where torque all values are known. Only value we are evaluating is sigma B, which is known as bearing stress or crushing stress. So this is also known as bearing stress. So if we are evaluating the sigma C crushing stress or sigma B, which is the bearing stress. So this equation you can rearrange and you can evaluate by substituting all the values. Then you will be getting the crushing stress as 2.39 megapascal. So which is well lesser than the allowable crushing strength of this flange material, which is lesser than 150 megapascal. So this is also safe. And finally we'll be evaluating the shear stress in the flange. So for evaluating or for checking the value of shear stress, we'll be making use of this equation, the torque capacity based on the shear of flange. So here you can substitute all the values in proper unit and find the value of shear stress induced in the flange. If you are substituting, you'll be getting a value of 1.33 megapascal, and the allowable shear strength of the flange material is 5 megapascals. So anyway, this is lesser than 5 megapascal. So hence this is also in a safest region. So we have designed, or we have found the all the dimensions of this shaft, key, hub, flange and the bolt used. So, and we have also checked for the stresses induced, and we have verified that it is in the safe zone. So this is the procedure for the design of a coupling, where it is a rigid coupling, and we have done the problem for flange coupling. So hope you understood, and thanks for watching. And in the next video we will be discussing about the design of flexible coupling, which is almost similar to this one.